Today's topic is the exponential form of a complex number. Let's start by taking a non-zero complex number z, which is say x plus iy. Let r comma theta be the polar coordinates of the point x comma y, which corresponds to this complex number in the complex plane. Note that since this is non-zero, this point is not the origin, and that is why its polar coordinates exist. Then you know these equations which relate polar coordinates with Cartesian coordinates. X equals r cos theta and y equals r sin theta. So if you now use these values back here in the expression for z, then z becomes r cos theta plus I r sin theta, or r times cos theta plus I sin theta. This is called the polar form of the complex number z. Note carefully that for this to exist, z needs to be non-zero. As you may know that there are infinitely many possible values of r and theta for a given choice of x and y, such that these two equations are true. And actually r can be negative also in general. However, in most applications and also in complex analysis, r is not allowed to be negative and is the length of the radius vector for z. That is, if you try to calculate the absolute value of z, that will be equal to r. So that's why we want r to be positive here, and that is why r equals the absolute value of z. And if you see the geometric representation for z and consider this radius vector which represents the complex number z, how do you get this radius vector? You imagine the point that corresponds to z, that is x comma y in the complex plane, and then consider the position vector of that point relative to the origin, that is the radius vector. So this r is the length of that radius vector. And the real number theta, of course, represents the angle measured in radians that this radius vector makes with the positive real axis. That means this angle. But is it really just this angle? It can be this angle also, no? Or even this angle, or even this angle. Which angle should you take as theta? And the answer is all of them. As in calculus, the authors next write, theta, here also theta has infinitely many possible values, including negative ones, as I said just now, because you are considering rotational angles, not just geometric angles. So this theta, for example, is a rotation that is anti-clockwise. So by convention it's positive, whereas that other possible theta like this will correspond to a clockwise rotation. So that will be negative, and they differ by 2 pi. There are other values also that I said moments ago. For example, this one, that will differ from this one by some multiple of 2 pi. That multiple may be a positive multiple, may be a negative multiple, anything can happen. But if you consider any two such values of theta, which are what actually, which correspond to rotations that start from the positive real axis and end here, okay, in any manner you can imagine. So any two such rotations correspond to two angles, positive or negative, depending on the sense of the rotation. They will differ. Their difference will be some integer times 2 pi. That integer itself may be positive, it may be negative. So for theta, we simultaneously consider all possible values. And all these values can be determined from this equation, tan theta equals y divided by x, which you obtain when you divide that equation involving y, that is y equals r sin theta, by the equation involving x, x equals r cos theta. And additionally, where the quadrant in which this point x comma y lies has to be given. Why is that so? That's because when you do this division, minuses may get cancelled. For example, say you consider the complex number 2 plus 3i, okay, or say let's leave that one. Consider the complex number minus 2 minus 3i. Alright. So for that complex number, that's a non-zero complex number, what will be the corresponding equations which involve polar and Cartesian coordinates? Minus 2 minus 3i is the complex number, which means if r and theta are the polar coordinates of the complex number or of the point corresponding to the complex number, then minus 2 will be equal to r cos theta and minus 3 will be equal to r sin theta. So if you form this equation from these two equations, what will you get? Minus 3 divided by minus 2. Someone may decide to cancel these minuses and obtain 3 divided by 2. So there you will get confused about whether the complex number lies here or in this quadrant. That's why the quadrant in which the complex number is must also be given. Only this equation does not tell you the full story. Each such value of theta is called an argument of the complex number z, and the set of all arguments of z is denoted by this notation arg z, where this a is small a, because there is a capital A also, it has a slightly different meaning. Note carefully that this is a set, it's not a single value. And among all the possible infinitely many values in this set, there is a special value that is called the principal value of this set, which you can denote by capital theta, which is that unique value which satisfies these inequalities. Keep in mind that all these angles are measured in radians. Minus pi less than theta less than or equal to pi, this is less than or equal to, okay. Here you have strict inequality, and this is also sometimes called the principal argument of that complex number set. There are infinitely many arguments, but only one principal argument which satisfies these inequalities. And we denote this principal argument by capital arg z. This is one single value. This is a set, and that's why small arg z, the set equals capital arg z plus 2n pi, integer multiple of 2 pi, where n is some integer. Sometimes this equation confuses us. On this side we have a set, on this side actually if you fix n, you have a single real number. Then what is the meaning of this equality? It's a somewhat bad way of saying what it is. Actually we should write arg z as a set in which the elements look like this, capital arg z plus 2n pi, and n varies over the set of integers. That is the real meaning. Note that if you have a negative real number z, then its principal argument will be pi, not minus pi. What's the definition of principal argument? It's the angle which lies between pi and minus pi. But even with those restrictions, in this case you still have two options. I mean, if you just simply somewhat vaguely give this restriction that it has to lie between minus pi and pi, that alone won't give you one value, because say the number will be here somewhere, say here, negative real number, so it will lie on the real axis and on this side. So one of the possible angles is this, which corresponds to pi because it's anti-clockwise rotation. There is another one, this one, that however is clockwise rotation, that corresponds to the angle minus pi. But minus pi is not an option, because theta needs to be strictly greater than minus pi. That is why we have to choose this option. So that's why the principal argument is pi. But this minus pi is one of the arguments. There are others also, of course. Another one would be this. There is another one, this. Infinitely many. But pi is the principal argument. Let's see this example 1. Consider the complex number minus 1 minus I, which lies in the third quadrant here somewhere I say, because I have not fixed the distance, unit distance, but it will be along this line, the line y equal to x in the plane. So it's here, and for this number the principal argument is minus 3 pi divided by 4. Let's see the two possible rotations here, which are the smallest that get us to this number. One of them is this one and the other one is this one. This corresponds to a negative angle because it's clockwise rotation. By what angle? Pi over 4, another pi over 4, another pi over 4. So minus 3 pi over 4. But if you take that other route, an anticlockwise rotation, that will give you this positive angle. 2 pi over 4s, 2 more pi over 4s, okay, so 4 pi over 4s and another pi over 4, 5 pi over 4. But this cannot be principal argument because it has exceeded pi. So this is the choice. You may have noticed that we are going somewhat hastily, okay, there is an urgency to reach the main part of complex analysis and we are not spending much time in explaining everything in full detail, and deliberately so because these are things that most of us actually already know. We are just reviewing these things, that's why. So the set of all arguments of this complex number will have elements that look like this: minus 3 pi over 4, that principal value, plus 2n pi where n varies over the set of integers. Next we do a peculiar thing. We give this complex number a new name. We write e to the power I theta in place of cos theta plus I sin theta. You know the meaning of this right hand side. It's clear to you. Theta is some real number. This is the cosine value of that. This is the sine value of that. And this is the corresponding complex number with this as real part and this as imaginary part. What is this? Is it the power of the real number e where the exponent is I theta? What does that even mean? Does it mean that we have to multiply this many copies of e and the number of copies is I theta? No, that does not make any sense. For now, this is only a shorthand way of writing this. In place of writing this, you can write this. That's just it. It's a new name. But why this strange name? The reason for this will be clear soon. And we also sometimes write in place of this exp of I theta. Exp stands for exponent. So now if you use this short name and write what z is, originally what was the polar form of z? R times cos theta plus I sin theta. So now it becomes R times e to the power I theta or exponent of I theta. This is called the exponential form of the complex number z. And needless to say, this also exists when z is non-zero. If z is 0, the polar coordinate theta does not exist. That is why we need z to be non-zero. So in this next example, if we consider that same number from example 1, that is minus 1 minus I, then it has the following exponential form. It is pretty easy to see that for this number the absolute value is square root of 2, which is the value of r, and for theta we can choose the principal value. So exponent of I times minus 3 pi divided by 4, which was the principal value. However, in this exponential form, it's not it's not that you have to it's not that you have to write only the principal value in place of theta. You can take any argument. So here you can actually take any argument. And do you also notice that it's a bit cumbersome to use this notation with this many things on top of e. So that's why we need this other alternate notation sometimes. So if instead of the principal argument you decide to use some other argument, then any argument looks like this in terms of the principal argument that we already know. So you can use this one instead. Now, why do we need exponential form in the first place? That is because when you write the exponential form, you have to write less. You don't have to write cos and sine, all those things. This form actually just tells you what r and theta are. That's why. It's like a nickname of someone. Someone might have a long name say there is a first name, a middle name and a last name. So we don't use the entire name to call that person every time. So instead we use a short name. It is something like that. Now next you look at these numbers e to the power I theta, which is just nothing but cos theta plus I sin theta. Its absolute value is 1. So geometrically where will it lie? It will lie on the unit circle centered at the origin, somewhere depending on theta. And from that fact, sometimes you can just simply know the value of such a number from inspection. Don't even have to consider cosine, sine, anything. From the figure itself you can know. In particular, these four numbers lie on that unit circle, 1, I, minus 1 and minus I. What should be e to the power I pi? This is a number on the unit circle which corresponds to anticlockwise rotation through an angle pi radian, starting from the positive real axis. Minus 1. That's it. What about this? This corresponds to a clockwise rotation because the angle is negative through this value pi over 2 radian. Minus I. What about this? This corresponds to a clockwise rotation through an angle 4 pi. Pi, 2 pi, 3 pi, 4 pi, 1. If you add 1 to both sides of this first equation, you get this Euler's equation, which sometimes is celebrated for how it involves 5 important numbers in mathematics: e, I, pi, 1 and 0. It looks mysterious, and especially to those who don't know the meaning of this. What mystery? This is just cos pi plus I sin pi. Cos pi is minus 1 and I sin pi is 0, minus 1 plus 1 is 0. So things look very mysterious and interesting once you don't know the meaning. Once you know the meaning, the mystery just simply vanishes. The magic is gone. Now let's next consider this circle in the complex plane. The absolute value of z is equal to r, where z is considered to be a complex variable. There are infinitely many possible complex numbers z for which this will be true. Which means what? These are all complex numbers whose absolute values are equal to r. R is some positive real number, and all of them lie at the distance r from the origin. So that's why all of them lie on this circle, which has radius r and has its center coinciding with the origin. So that's why this is the complex equation of this circle. And you can use the exponential form to write a parametric representation of the circle, a parametric equation, which looks like this. Why? That is because if you take the absolute value on this side also you take absolute value, and absolute value is multiplicative. So the absolute value of this equals the product of the absolute values of this and this. This is a complex number of absolute value 1, so that's why that vanishes. R is the positive real number, so its absolute value is R itself. Okay, and here the parameter is that theta, which you bound between 0 and 2 pi. So what happens is that when you take theta equal to 0, what is the thing that you are getting here? Don't try to think in terms of exponential function, okay? This is cos theta plus I sin theta, don't forget that. Cos 0 is 1, sin 0 is 0, so that means this is 1. Although if you think of it as an exponential function, still you get 1, that's the different thing, we will come to that afterwards. But it is 1 nevertheless. So we get z equal to r, so the point is here. And then as theta increases from 0 and then finally reaches 2 pi, the point rotates like this, while all the time being at that same distance r from the origin, and in doing so it traces the circle in the anticlockwise direction, and by the time it reaches 2 pi, it comes back to its original position. So in that sense, this is a parametric representation of this circle. We are going to need this type of things when we do contour integration. And more generally, you consider this other circle which also has radius r, but now its center is at the complex number z0. This circle has this parametric equation. If you write what this z minus z0 is, then it will be r times e to the power I theta. So then you add z0 to both sides and you get this parametric equation, where again of course theta varies from 0 to 2 pi. Now you may wonder why exponential form? I mean, what is the role of this e here? Why have we suddenly chosen e out of nowhere? Because we originally had what? Cos theta and sin theta. Cos theta plus I sin theta. Why e? That will become apparent slowly. In the next complex analysis video, we will see what happens when we multiply two such numbers, e to the power I theta 1 and e to the power I theta 2. And that will give you some idea of why we have chosen this. Actually, there is a surprising link between this cosine and sine function and exponential function, which is not apparent when we restrict ourselves to real numbers. But it slowly becomes apparent when we consider complex numbers.